Good morning, everyone. Welcome. My name is Jason Yates. I'm the Technical Services Manager for Riello UPS Systems. I hope you enjoy my presentation. I hope we find it informative, and obviously we can discuss it later at the end. So, as we know, the data center industry is one of the fastest growing and transforming industries of the last decade. We've seen transformations in terms of ecosystems, technical and regional requirements, systems and architectures, power demands, efficiency, and of course, the total cost of ownership. Now, as a result of these transformations, obviously, the data center industry is becoming under the spotlight, having become very power hungry and obviously costly to operate. In addition to this, we had 150 countries signing off the COP agreement by 2030, obviously aiming to reduce the global temperature by 2 degrees, in addition to the strong CO2 reduction targets of 2030. Basically, we can say that sustainability has become one of the main challenges for humanity at this time. In addition to this, we obviously have inflation, we have the geopolitical instabilities, and obviously the related energy issues that we see. We have industry supply chain difficulties, which haven't gone away since COVID. Basically, the industry is facing substantial, strong headwinds in terms of and making the whole business even more challenging. So the question we ask is, how we as Riello, as a UPS manufacturer, can help the data center industry become more sustainable, achieve net zero, meet the requirements of scope emissions, whilst at the same time, obviously, reduce operating costs. Well, we can start by looking at the power demand and obviously how the very latest and high efficiency uninterruptible power supplies can dramatically reduce the energy loss, the cooling requirements, the operating costs, and ultimately the CO2 production. But also we can look at obviously the total cost of ownership and how advancements in UPS design can help reduce costs by using high quality, long life components, provide user flexibility, and obviously, again, reduce overall maintenance costs. So what we can do first of all is let's take a look at power demand and high efficiency and the double conversion UPS system. Well, a UPS's efficiency is defined as being the active power at the input versus the active power at the output, which is measured in watts, kilowatts, or megawatts, depending on the size of UPS. The difference between the input and the output power is effectively lost energy, which is completely wasted unless, of course, it can be recovered. Now, this wasted energy is mostly converted to heat, which generally needs to be removed and or be cooled, which again takes more energy. Basically, the greater the energy loss, the lower the efficiency, the higher the costs. Now, obviously, every UPS manufacturer, we all ultimately strive to produce a UPS that can achieve 100% efficiency. Sadly, however, due to current technology and, of course, the laws of physics, it's simply not possible at present, albeit through advanced UPS designs and the very latest in component technology, we are getting very close. So before we start looking at the effects of efficiency, I just want to tell people exactly how an online dual conversion UPS works and why efficiency is so important. Well, on the screen there, you can see that's a typical diagram of an online dual conversion UPS system. On the left-hand side, you've got the main supply input. On the right-hand side, you've got the output to the load. At the bottom there, you've got the batteries, which obviously provide power to the UPS when the main supply fails. And at the top, you have the bypass line, which can be used for various operating modes during emergencies or during maintenance periods, etc. Now, the system is so-called, it's referred to as the online dual conversion or the online double conversion UPS. The term dual conversion comes to what we do within the UPS system. Basically, what we do is we take the main supply that comes in, we convert that AC into DC. So that's represents our first conversion. Then we take that DC and we reinvert it. So we recreate the AC waveform from DC back to AC again. And basically what we do is the system is referred to as being online. The reason why it's called online is because basically the inverter is permanently supplying the power to the critical load. Now, the reason why we do this is basically because all of the nastiness of the incoming main supply gets filtered out and we produce a completely clean waveform for the critical load. Unfortunately, however, the online dual conversion UPS system, albeit it provides the very highest levels of protection for the critical load, Unfortunately, because of the conversions that we produce within the UPS system, it also produces the lowest efficiency levels in terms of operating modes. Now, to address this, many UPS manufacturers, including ourselves, we can operate the online dual conversion UPS system in different modes of operation. One of these modes is eco mode. Now, eco mode is so called because basically it obviously provides a high level of efficiency. And the reason why it does that is because basically the load is being powered directly through the bypass line. And because we're not producing or we're not performing those two conversions, we haven't got the same losses through the UPS system. So a typical UPS of this type can be running up to 98.5, 99% efficiency, albeit there is a downside to this, which I'll come to in a second. We are still performing some conversions because we're still taking AC power in, because we've still got to maintain the batteries and the systems within the UPS system. So things are still running in the background, albeit what we can say is eco mode in this time now provides the highest levels of efficiency. The downside to eco mode, it provides little to no protection against network disturbances because effectively the load is connected directly to the input. And also, when there is a main supply failure, there are switching breaks. So effectively, as it takes time for the UPS system to come online, there is a small break. Traditionally, there is a small break in power to the critical load. So again, it's not a favored mode of operation. We do have an operational mode that sits sort of in between eco mode and the online mode. And this is an active eco. Some manufacturers will give it all different kinds of fancy titles, but basically we refer to it as active eco. It's very similar to eco mode in that, again, the load is being powered directly through the main supply. But this time, the dual conversion process is still operating. And effectively what's happening is the inverter is actually running in parallel with the bypass line. So effectively, it's operating like a power conditioner. Now, by doing that, it can provide some forms of power conditioning, but again, it obviously doesn't provide the protection as it does with an online system. And so what we can say about active eco mode is that it now provides a medium level of efficiency, somewhere between eco mode and obviously online mode. It does offer obviously some power conditioning in terms of power factor correction, SAGs, THDI correction, and so on. But again, because of this direct connection, it does offer little to no protection against network disturbances. So again, it's not a favorite choice. Now, with an online UPS system, obviously providing the very highest levels of protection, basically nearly all DC managers will operate their online UPSs permanently in online mode in order to minimize any potential risks. So when comparing UPS efficiency, we must always compare like for like. Otherwise, we can't establish a true baseline in performance and obviously the potential savings that can be achieved through high efficiency. Basically, we can say that anything other than true online can be a bit of a gamble to a DC manager. Now, a lot of the time you'll hear the term banded around about an average efficiency figure. Now, you've got to be careful with this because an average efficiency figure is not the same as an online figure. Basically, average efficiency is typically a combination of those operating modes that we were just talking about. And basically, for example, a UPS system could be operating over 24 hours. And for, say, 12 hours of that, it could be in online mode. And for the remaining 12 hours, it could be in eco mode. And unfortunately, because of this, the average efficiency is not really a true representation of real life conditions. And so the average and online figures can't really be compared. Unless obviously you're operating it that way. But basically the average figure will always show an exaggerated efficiency level, which can be somewhat misleading. Now, high efficiency UPSs, on the other hand, obviously can achieve extremely high efficiency levels, even in online mode. So there is no need to settle for average performance. What I want to do now is just want to have a quick look at a typical high efficiency modular UPS. Now, unfortunately, this is a blatant sales plug on my behalf. I do apologize. But this is an online double conversion UPS, which is produced by Riello, obviously, providing a true online efficiency higher than 98%. The system is basically the multi-power 2. It's a flexible, scalable, resilient, and a sustainable UPS system. It's built around a high efficiency 67 kilowatt power module. Now, this 67 kilowatt power module, it can be combined with 3 different power frames. We have a 500 kilowatt power frame. We have a 1 meg to 1.25 meg power frame, and then we have a 1.6 meg power frame. Now, basically, these cabinets can all be obviously connected in parallel with more power frames, so we can increase the power still further. Now, if we take a look inside these cabinets, basically you can see they've all got a very, very similar layout, but they're built around the hot swappable power modules that can fit inside all of the cabinets. The same power modules is used throughout all cabinets. There is space for redundancy for obviously redundant systems. They have a fully rated bypass system in the eventuality of problems. And still further, in terms of their flexibility, the beauty of this product as well, it's not just about the efficiency levels as well. It's basically its flexibility to be installed in various environments. If we take a look at the 1 meg and the 1.25 meg, you can see that we've still got the same hot swappable modules. We've still got the same space for redundancy. In this case, you can have it with or without switches, because believe it or not, even the switches alone will create changes in the efficiency because of the losses through the switch. So basically, as much as we can, we can make the efficiency changes within the UPS system, you've got to look to the overall infrastructure to see what else can be dissipating heat effectively. In addition to this, we can add in back feed protection. So the system is extremely flexible for most of data center environments. So enough of the sales plug. Let's move on. Okay, so how have we got to where we are today? Well, many, many years ago, we used to produce UPS systems using what's referred to as a two-level architecture. Now, the two-level architecture back in the day, it's been a stable design of UPS for many, many years now, but it could only achieve an efficiency in reality of up to around about 96% at best. We then made the move from the two-level architecture into the three-level architecture. Now, the benefits of the three-level architecture is that we could push the efficiency up to 96.5%. The downside to three-level architecture is it requires more components, it requires more processing power. So unfortunately, the three-level architecture traditionally would only be seen in larger UPS systems, say 200, 300, 400 kVA and above. But nowadays, you will see this technology in UPS systems as small as 10 kVA because processors have become more powerful and designing these systems has become more easy and more compact. The next phase of evolution was to improve the design of the filter components. And by improving the design of the filter components, it enabled us to push our efficiency levels now up to around about 97%. So we're getting somewhere closer now. Now, the very latest change to UPS design and recently introduced, and this is all primarily driven by the EV market, is the move from traditional silicon components over to silicon carbide components. Now, again, same design, but we are now, instead of using a traditional IGBT, we're now using a silicon carbide MOSFET device, which again, very commonly used in the EV markets. Now, the benefits of silicon carbide, it can produce efficiency levels up to 98.1%. In fact, during testing at times, we've pushed even 98.2%. So how is that being achieved? Well, if we look at these tables here and the graph, basically the table at the top there is showing a comparison between a traditional IGBT and a silicon carbide device. Now, as you can see there, the total chip area, basically, the silicon carbide device is around about a fifth of the size of a traditional IGBT, so it makes our designs much smaller. The conduction losses are slightly higher for the silicon carbide device. In fact, they're roughly about the same, but again, slightly higher. But our switching losses are where we make our gains. As you can see, the switching losses through a traditional silicon carbide device are around about a quarter of that of a traditional IGBT. So in total, overall, we are producing around about 50% less heat than a traditional IGBT. Also, the junction temperature can run cooler as well. In the graph at the bottom there, this is basically showing a comparison between 4 different load levels, 10%, 25%, 50%, and 100%. And as you can see, the silicon carbide devices outperform the traditional IGBT in all areas. So it's not just a particular sweet spot. So what is it that silicon carbide can bring to the party? Well, what we can say is there are less losses. That produces less heat. That requires smaller heat sinks. The systems become smaller. They have excellent thermal management. This reduces component stresses. They have a very high power density because of their size. And because of the smaller components, it equals a compact design. And because we can do this, we've now got ultra high efficiency UPSs pushing 98.1%, again, independently verified. And also we have increased reliability, which is obviously extremely important with any UPS system. If we look at the actual efficiency curve now of the devices, like all the devices, all manufacturers will produce curves like this, we can see that Between the load levels of 25 and 50% load, we are pushing an efficiency greater than 98%. So it's great for an A and a B system installation. If we widen that load level still further, you can see between 15 to 80%, we are still pushing efficiency levels of greater than 97.5%, which again, extremely very high. Going further afield again, between the load levels of 10 to 100%, we are pushing efficiency levels up to and above 97%. And again, the beauty of this is when the UPS system is in true online mode. This is not an average efficiency figure. So we can say what savings can actually be made by using silicon carbide. Well, as we know, reduced heat output means reduced wasted heat, means reduced cooling requirements. That basically reduces overall energy costs and obviously the subsequent environmental impacts that come along with that. Because we're utilizing long life components, maintenance-free capacitors, and the system have a high mean time between failure, MTBF, and a low mean time to repair, MTTR, we have reduced maintenance costs. And again, the associated impacts of this includes removing waste components and so on that have been replaced. Now, it's not just purely in terms of the energy side of it. We've considered the savings. We've also looked at the overall design of the power module. Obviously, we know it's high efficiency, 98.1%, 67 kilowatts in 3U, so it's very small. It can operate in temperatures of up to 40 degrees C with no down rating. And the beauty of this, again, this keeps our cooling requirements low. It has a large charging capacity, so it can be partnered with large battery systems. Whether that be lead or lithium, whichever. It's easy to handle. Okay, 37 kgs is heavy, but compared to some modules, it's extremely light. It's fully independent. A hot swap of these cap modules can be changed live, so maintenance and repairs are done quickly. It has full firmware and parameter auto alignment, so you put a new module in, it automatically updates for you or gives you the option of how you wish to proceed. And again, fully fault tolerant. It's important that these modules don't propagate faults through onto other modules, and it's mechanically barriered as well. So it's not just about that, but we've also looked at the optimization in terms of the manufacturing and the operational architecture of the module. The module has been built with a simplified and clean layout, which enables quick and easy construction, close connections for reduced losses. It's got humidity and temperature sensors. It's got input air temperature sensors. They have capacitor temperature monitoring, and they have power factor correction and inverter temperature sensors per phase. Basically, we've implemented a full thermal map for monitoring and predictive maintenance. But most importantly, we've designed and built with the low carbon footprint in mind. So in terms of it's not just the energy and the optimization, we've got to look at the maintenance costs. Now, we've used long life components in these systems. So effectively, there is no capacitor replacements required over the lifespan of the system, which would typically be 15 years. Now, normally what would happen is you would have every 5 or 7 years, a traditional UPS system would require a fan and a capacitor change, let's say year 5 or year 7. So over a 15-year life, a traditional UPS would have the capacitors changed at year 5, then again at year 10. So obviously there's a cost to that. In this case, worst case scenario, the system will only require a single fan replacement in its lifetime, which would be around year 7. But it would certain criteria would dictate that that would never be needed because, again, if it's not used in a heavy environment, then that you may never have to change those fans. Most importantly, there's controllers that carefully monitor all of the consumable items, providing a full comprehensive diagnostic system, making maintenance and repair quick and efficient. So how does a high efficiency double conversion UPS system affect the total cost of ownership? Well, if we look at the power that's been the cost of running a data center, as you can see, traditionally around about 60% is taken by the energy cost, the running costs of the data center. And around about 30% of that is taken in terms of the operation and maintenance costs. You've also got obviously spare parts and space rental, but they're the two primary areas where the costs are involved. And that's why we've actually, we've pushed it into not just the environmental impact, but we've specifically designed around these two areas. If we look at the savings that can be achieved by deploying a high efficiency UPS. Now, this is an efficient UPS system, a new system. where you've got a 98% efficient UPS versus a 96.1, which is still a very high performing UPS system. But just to show you the comparison by installing these two systems, if we deploy the 98% efficient UPS instead of a 96% efficient UPS, and we based our calculation criteria, I want to be open about what we base this on, but based on a 1.25 megawatt UPS with a 1 megawatt load, we've based it on a pence per kilowatt of 15 pence. Obviously, it depends on the various sites and the customers. Cooling coefficient, we've put at 2.5. Obviously, this can change depending on sites. We've done a CO2 per kilowatt hour of 0.233. We've done a climate control levy of 0.775. I've done an annual decrease in CO2 production of 3%. Again, this can change, but we can vary that. I've done an annual electricity cost inflation of 4%. I've not included for reactive power because this is typically showing two new UPSs, which would have a very good input power factor anyway. But obviously, if you were deploying a new UPS in relation to an older machine, like an old 12 pulse or something like that, then obviously reactive power would come into that. I've not included for maintenance costs because I'll look at that shortly later. But at those load levels, traditionally, the high efficiency machine will be running at around about 97.5, and the lower machine will be running at 95.5. And that would basically equate to a typical annual savings of around about 264,000 kilowatt hours per year. That would come out at £42,000 saved a year, which again over 15 years would come to £833,000, resulting in 61 tons of CO2 saved over a year. Again, over 15 years, 715 tons. Obviously, these numbers would massively change depending on the installation type and so on. And if it's a legacy equipment, they can be nearly double or even triple. Now, the problem we find is that there's a bit too much emphasis put on the initial capital expenditure when building a new data center. However, you've got to agree that the money that can be saved at day one is insignificant compared to the operational expenditure savings over the life of the data center. And we see design specifications will typically define a minimum efficiency level just to put a tick in a box. I'm not saying that everybody does, but then rarely consider the long-term benefits of using higher efficiency systems. So what we can say is basically, if cash really is king, then let's make it so, but for the better of the environment, and not try to pass the problem on to somebody else. So in terms of those the cost savings, we can also look at the maintenance cost savings as well. And I can say that basically based on component costs alone, this is not taking into account labor and so on, a typical installation of 1 megawatt could provide an operational saving in excess of 80 to 120,000 pounds over a 15-year period. So again, significant savings to made. Now that doesn't include the batteries. Because of the advanced diagnostics, this dramatically reduces engineers' time on site, thus reducing costs through resource requirements, travel, fuel usages. The system is true hot swappability, so it makes repairs quick and simple for on-site engineers in order to maintain the resilience of the system. And a low mean time to repair of less than 30 minutes ensures that any maintenance and the costs of contracts are kept to a minimum. So what can we say in summary? Well, always compare like for like. Average is not a true online figure, so always read between the lines. Don't just consider the CapEx. Look at the OpEx savings, as these are far higher. More savings equals a faster payback. These can all be calculated based upon a specific application. We've got significant low repair and general maintenance costs. We have significant CO2 savings. We have a smaller space requirements and footprint. We have reduced cooling requirements. So basically, we can say that by installing a high efficiency UPS in place of a UPS with, say, 96% efficiency, a typical installation of 1 megawatt could provide a saving of around £1 million over 15 years. So that is why we've decided to go towards a smart, scalable, and sustainable power. These UPSs are designed and manufactured by Riello, Italy. And thank you for your time. I hope you found my presentation informative, and I would like to take any questions should you have any.
Thanks so much, Jason. So really it's about thinking sort of long-term savings and thinking ahead rather than in the here and now in this case.
Yes.
I just wanted to go back to, you talked a little bit about the silicon carbide coming from sort of the electrical vehicle. So obviously with UPS being so efficient at the moment, sort of any gains we're going to make is going to be really incremental. So is that kind of where we're looking for how we're going to make improvements, and what will those technologies look like? Where are we going to be finding the improvement, finding the efficiency gains in future, and from where are we going to be getting them?
I think the way the things are getting, obviously, as we know, as we get closer and closer to 100%, it gets more difficult. It's always going to get more and more difficult. But obviously, we are getting to the point where we're purely just down to the losses of the conductors. So in terms of the gains, obviously more gains can come in terms of trying to developing new operational modes, which enable us to provide much higher efficiencies, trying to maybe possibly get to eco modes where they can be more protected and resilient is another one. But again, it's just advancements in technology effectively, especially, and obviously it's all been driven from the EV market, especially the likes of Tesla and people like this who use this component, because obviously the technology existed many years ago, but it's only till now that it's actually becoming available in the voltages and power ratings that are required by the UPS industry. Sorry. Go.
So I was going to say, I suppose once you've seen it used in a practical application, then it's easier to then apply it to other industries. And
it's got proven reliability. This is good. This is the most important thing in terms of UPS systems.
And what about in terms of like developments on the battery side of things? Like, is that also going to play into
Yeah, so obviously the main things around the battery, obviously everybody's bounding around the lithium aspect of things, but obviously you've got the lovers and haters of lithium. So it's a difficult one to call. Obviously lithium does have it does have a future, but I don't think lithium is the final way to go. I'll be honest with you, it's a stepping stone which is going to push us up to new technologies, which is like anything with electric cars. It's a stepping stone. Obviously we have lead. Lead has been around for many years. Obviously, it's robust, it works, it's trusted. You've got obviously the likes of pure lead, which again, obviously improved performances. But yeah, in terms of technology, yes, I think it's more of, obviously I'm not buying into chemistry, and I don't know the technology behind the chemical of the battery. But yeah, I'm not sure, to be honest with you. I'm not sure lithium is the way. I'm not convinced myself, but it has to be there as an option. People want it as an option.
And so just as I asked that, we got the question of what are your thoughts regarding lithium versus lead acid TCO. So
yes, it's, to be honest with you, I'm currently working on some TCO numbers for lead versus lithium. You can look at lithium with a traditional, maybe a 20-year life. Still got electronics in there at the end of the day, which still obviously still wears down. So if you put a 20-year lifespan on your lithium, you've then got to weigh up whether or not is it just cheaper to replace your lead multiple times as opposed to using lithium. But we're currently actually just working through a lot of TCO calculations for lithium, because it is, I think a lot of specifications, again, like I say, they will request, lead and also a lithium option. But, the take up on lithium is extremely small, but it is happening. But for me, I'm 50-50. I'll be honest with you. I wouldn't want to commit.
So staying on the fence while you can.
I'm staying well on the fence. I'm not going either side. So,
okay, thank you so much for joining us today, Jason. That was really great. Just want to say, it's not a question, but we did have someone say that was a really interesting presentation. So thanks so much for joining us today.
You're welcome.
And I hope you have a lovely rest of your day.
Thank you very much. Have a great day.
Thank you.